will discuss basic electrical machines. So electrical machine is can convert electrical energy to mechanical energy, or else mechanical energy to electrical energy. So we have motors which are converting electrical energy to mechanical energy, and we have generators which converts mechanical energy to electrical energy. So we will learn about motors and generators, but just one type of generator and one type of motor. Okay, so there are different types of motors and generators. We just discussed one type each. So there is a coupling system, coupling field to convert the electrical energy to mechanical energy. This coupling field should be able to store energy and transform it to a different form. And apart from a motor and a generator, you will learn about the transformers as well. Okay, so transformer is just, it's not converting electrical energy to mechanical energy, it is electrical to electrical. So your input also electrical, output also electrical for transformers. But transformer can step up or step down. So if you have when we generate electricity from the plant, we use a step up transformer to set up, and then it transport to your households, because when it is transforming, before it is coming to your households, there is a step down transformer to lower the voltage. So we increase the voltage and we lower the voltage. We can increase or lower, step up or step down the voltage using transformers. And also transformers can be used to electrically isolate some part, because I will show you when we go to the transformers. So we will learn about one type of a motor, one type of a generator, and transformers. Are we good? Any question? Okay, now we have discussed about energy storing devices. Do you remember the energy storing devices we have discussed here? So we have discussed about the capacitors. So energy is storing in an electric field. I hope you remember this. And in a capacitor, energy stored in a capacitor, we can find it. We can find it using this equation, half times the C, the capacitance times the V squared. And also we discuss about the inductors, which is a current carrying coil, and it is storing energy in a magnetic field. That energy can be found using this equation, half times the L times the I squared. So we are learning here, I told you, electrical machines, which is motors, generators, and transformers. So we will discuss about I told you one type. So we will discuss DC machines. We will discuss about DC motor and a DC generator. And transformer is a AC machine. So AC, you know what is AC. So the voltage and the current is changing with the time. And we are learning about the transformers. Okay, let's start with the transformers, and then we'll move to the generators and motors. So transformer is converting. It's not converting electrical to mechanical. It is input, or it is an electrical, and also output, also an electrical. So it's a static machine. So that means you don't have any moving parts in a transformer. But when you consider generators and motors, we have moving parts, rotating parts. But in transformer, it is a static machine. It doesn't have any moving parts. So it consists of two windings, and it's a metallic core. So you can see we have a metallic core. So metallic core is this. This is a metal core, and we have this our primary side input, and this is our secondary part, secondary winding. So you can see we have a winding in the primary side. So winding in the primary side has NP number of turns, and for the secondary side again we have a winding which has a NS number of turns. So these N's can be anything, like, you know, in the questions this will be given to us, or else we have to find it using the theory. So we supply a current, AC current to the primary side. So we know there is a current, it is AC, and there it is going through a resistance in the primary side, and it is when it is going in a current carrying coil, it produces a magnetic field. Do you agree with that? When we have a current carrying coil, it produces a magnetic field. That magnetic field is going like this. The direction of the magnetic field you can find using the right hand rule from physics. Am I right? So when you turn your fingers in the direction of the current, the thumb gives you the direction of the magnetic field. So this magnetic field is moving in the secondary side. Because of this magnetic field in the secondary side, it induced a current in the secondary coil. So we supply a current to the primary side. That primary current induces a magnetic field, and that magnetic field is producing a current in the secondary side. So do you understand what is happening here? Is it clear or not?
So basically it's like moment in physics. The electric field, the magnetic field. It's like the rotation.
It's nothing rotating here, just the current is moving along the coil. So you have a current carrying coil now, so the current is moving around the coil. So when there is a moving, current carrying coil, that induces a magnetic field. So that magnetic field is this one. So there is a magnetic field in going like this. So there is a magnetic field means you have a north and a south, so that it is the field lines is going from north to south. So it's simply like this. So you have a current carrying coil. When you have a current carrying coil, it induces a magnetic field like this. Isn't it? That's you have done in physics, if you can remember. That magnetic lines are going along this path. So that lines, when you have a current carrying coil, it induces a magnetic field. Similarly, when you have a magnetic field, it induces a current in a current carrying coil, in a coil. So this magnetic field, which is going towards the secondary side, that produces a current in the secondary winding. So there is a current produces because of the magnetic field. So that current we call the secondary current, and it is going through any load we have. So the resistance in the secondary side. So this is the theory behind, or how the transformer works. So do you understand it, or do you want me to explain again? Are we good? Okay. So let's see how we can do the calculations with the transformer. So we have some notations here. So EMF stand for the induced EMF, electromagnetic force, but it's like the voltage. Okay, so if you are familiar with the voltage, so you can consider it as the voltage. We use the E because it's an induced voltage. So anything in the primary side number of turns, NP. Primary side voltage is EP. Primary side current is IP. Similarly, when you have secondary side, the number of turns in the secondary side is NS. EMF induced in the secondary side is ES, and the current in the secondary side is IS. So we have these notations. P stand for the primary and S stand for the secondary. Okay. So the theory behind is induced EMF, or else the voltage per turn, is equal in both the sides. So if you consider E in the primary side and the E in the secondary side per turn, if you divide by the number of turns, these two are equal. So this is the theory behind the transformer. If there is no loss, so you always get ideal transformer. In the ideal situation, we consider there is no loss in the magnetic field. It's totally going along the secondary side. So for an ideal situation, we can use this as a known equation. Are we good? Any question? Okay. Can I move to the next slide? Okay, so there are three types of transformers. One is step-up transformer, where your secondary side voltage is more than your primary side voltage. How this one is happening? When you have more turns in the secondary side, than the primary side. For example, we have 100 turns, 100 number of turns in the primary side, and you have double the turns. So you have double the turns in the secondary side, 200. So if your voltage is 100 here, your voltage will be coming double in the secondary side. It will become, so let's say 200 volts. The secondary side will be 400 volts. Why is that? We know per turn the voltage is the same. So if you divide the voltage by the number of turns, it is the same in both the sides. Am I right? So this we call a step-up transformer. So because you are stepping up the voltage, so your input voltage is 200, but you are doubling the number of turns in the secondary side. So you can make the voltage to 400 in the secondary side. So this kind of a transformer, we call that a step-up transformer. So we need to do the stepping up. When you produce the electricity in the plant, it should be step up and it should transfer to minimize the losses. So we have a step-up transformer near the generating plant, so that it is stepping up before it is transferring to the households. Step down is opposite. So what do we mean by step down? Your number of turns in the primary is yes, so I need to change this. This should be in the other way around. So your primary is this way. So your secondary is less. Okay, so it's a printing mistake. So primary number of turns are more than the secondary number of turns. So for example, if you have 400 turns NP in the primary, and if you have just 50 turns in the secondary, your voltage is less. So here if you have 100 volts, here you only have 25 volts. So it is stepping down. Do you understand it? It's stepping down by 4 times, like 1/4. So this kind of a transformer is needed before we get the electricity from our wall socket. It should be stepped down, because we have 230 in Australia, isn't it? So we have 230 volts from the wall socket, so it need to be stepped down. So, and also we can have same number of turns in the primary side and the secondary side. So these ones we need wherever we need a electrical isolation. So for example, we need to keep this space without any electrical field. There can be some situations like that for medical equipments, or maybe for safety or security purposes. So if you want to keep this area without any electric field, you can have a transformer from this side and a transformer from this side. So electrical field is only this one and this one. This is a electrically free area. So you are not stepping up or stepping down. You have the same voltage, same number of turns in the primary side and also in the secondary side, but you have an electrically isolated part in between the two sides of the transformer. Make sense? Yes.
When N is more than NP,
Yes.
therefore EN is more than EP.
Yes.
It does make sense, like, because when we have the formula EP over NP, right? E equals TS over NS, we can cross times, right?
Yes.
NS, EB, and ES, NB.
Yes.
So when NS is more than NB, so EP is going to be more than ES. Why EP is more than?
Yes, because you write it and find it out. So if you have, so you have this. Am I right? This is what you have. Sorry, this is what you have. So per turn, the voltage is the same. That's what it says. So for example, if you have, tell me this. So if this one is 50, okay, and if this one is 100, and if this one is maybe we'll take 50 as well. Okay, so can you find me NS, please? NS is what? So what is it? 100. Okay, so when your your NP is less than NS, isn't it? So do you get what I mean? So when your EP is 50 and NP is 50, your ES is 100, then your NS is 100. So you can see when NP is less than NS, your EP is less than ES. They are not equal. They are not equal. Are they equal? This is 50 and this is 100. I ask you to find the NS. You can, EP is 100. Okay, if your EP is 100, find me the NS now. NS will be 50. Okay, you want to make it like, you want to make EP higher than ESO, EP, what do you want to see now?
I want to see it because when N is more than NP.
Okay, NS is more than NP, is that right? Yeah. Okay, so I'll give you numbers. Okay, so you figure it out. You need to have NS more than NP. Am I right? So let's take NP. NS is whatever the number you want. You say this is 100 and this is 400 and 100. Is that fine? Okay. Now your wall, you need to find out these two. Is that right? We need to know one. So let's take this one as ES as 100. Now can you find EP, or else let's say this. EP is 50. What is your ES? 200. Is this right or wrong? Is this relationship right or wrong? Is this relationship right or wrong? Right. So do you want to check more numbers, or are you agree with this relationship? Okay. Okay. So let me. What do you want? NS is 100. NS is 100 and NP you need to be 400. Okay. Now find me this. Now find the ES, please. No, I made an announcement. Did you get the announcement? And your timetable, if you look at your timetable, practically is next week, not this week. Yes, next week. And I made an announcement. You guys need to check your announcements. Okay, so did you go there? Yeah. Are there any more people? No. Yeah, I need to check as well if there are more people. I have to bring them here. I'll give you some questions and I will go and have a look. Okay. So this one is the last one. This is the last topic. Yes, we can do a revision next week. This one is what? Okay. Now what can you say? Do you agree with this relationship now? Is this one? Now you have NS is less than NP. Am I right? Do you have this relationship proved? Is that proved now? Are you happy with both these relationships? Okay, so that's good. No more conflicts, right? Okay, that's good. Yes, when you have something doubt, you need to sort it out. Otherwise, we will think about it and we don't pay concentration to anything else. You happy now? Okay, that's good. Okay, all right. So we'll move on to the next part. So we can have step up or step down. If you want to make a step up transformer, what should have? We should have more turns in the secondary side. If we need to do a step down, we need to have less turns in the secondary side. Okay, so if we have the same number of turns in the primary and the secondary, it is electrically isolated part. Okay, can I move to the next slide? When we do a question, I'll explain this theory again, okay? Then you will be able to catch up. Okay. Okay, so we know already. I already told you this relationship. And this we call the turn ratio. So it's a definition. So we define something called turn ratio, that is equals to the number of turns in the primary side divided by the number of turns in the secondary side. So according to the energy conservation, so we are dealing with ideal transformers where there is no losses. So energy, do you remember the power equation? So if the energy is equal, then the VI in the primary side should be equals to the VI in the secondary side. Okay, so you can use this equation as well because we are only dealing with the ideal transformers. And also we can find the magnetic flux. You can find the magnetic flux using this equation. You can do it, frequency will be the same. So you know frequency, we discussed about the frequency. Number of cycles per second. So that is the frequency. Frequency in the primary side and the frequency in the secondary side will be the same. So you can use this equation to find the flux. So that's the theory behind. And the flux is measured by Weber's, WB. Okay, we'll do a question, then you will be able to understand it more, okay, with the numbers. Okay, can I move to a question? E is like the V, okay? E is the induced EMF. It is like the voltage. You can use the Ohm's law to find it. If the resistance is the current and the current is not, you can use the Ohm's law to find it. Okay. Done. Okay, so we'll move to a question. Okay, can I give you a little bit of time for you to try this one? Then I will explain you. So there are two situations here, no load and full load. For example, let's take a fan. So for a fan, when the fan is switched off, no load means fan is not rotating. It's just an example for you to understand what these two are. So there are two situations talking about here. One is no load and the other one is full load. So no load means there is no current drawn, or else little current is drawn. So this one is full load means its fan is moving with the full speed. So you can turn it to different speeds, isn't it? When it is turned off also, there is a small current. That means the small current is drawn. That is no load. And that is two different situations. You can consider it as two different circuits. Okay, so first do for no load, please. So an ideal transformer has 300 turns in the primary side. So you write down these things. When you have a transformer question, write down these things. So NP is given as 300 and NS is given as 600. The primary is connected to so primary side voltage or the EMF, EP is given as 240 volts. And the frequency is the same for both the sides. Okay, so 50 Hertz. Secondary winding supply. So secondary side current is given to us 5 amps at a lagging power factor. So there is a power factor of 0.8. That means it's given here. So this means voltage is equals to our output power. They have given you the output power. PS is Vs times Is times 0.8. So that's also given. There is a lagging power factor and the power is this. So these are the information you no, they are not talking about full load or no load in this question. Okay, it's good. So I want you to find these ones. So turn ratio is what? NP over NS. Did you write down these equations? You don't need to remember these equations, will be given to you, but if you wrote it down, it is easy. Current in the primary side, the power supply to the load. Load means load is always secondary side, okay? Maximum flux. So do you remember the equation for the flux? It is, any of you wrote it down? It's 4.44 frequency. Yeah. Or else you can have, instead of P, you can have S, okay? Both gives you the same. Okay, so I will give you time. I want you to find this A, B, C, and D. Turn ratio is number, and turn ratio doesn't have any units. Number of turns doesn't have a unit, so number of turns divided by the number of turns, it doesn't have any units. Current is amps, voltage is V, power is, you can have the power, watts, this is Webers, WB actually. Yes, you have that equation as well. So EP VP is equals to ES VS. So you can easily say the EES. What should be the ES? Your number of turns are doubling. Am I right? So your voltage also need to be doubled. So this should be 480 volts. Agree? Do you agree with that? Did you get this? Yes, it is doubling, so it should be doubled. Okay, now turn ratio you can easily find. Turn ratio is what? Half, am I right? 0.5. Okay, so turn ratio we found. Current in the primary side, how do we find the current in the primary side? You know the voltage. How do we find the current?
It's EP times IP equals to RS.
Yes.
So EP is equal to ES times RS divided by
Yes. Oh, so what did you get? So this one power you can find. Power is equals to Vs, which is 480 times the current is 5 times is 0.8, and that power is what? Power supply to the load. What was that?
2400 watts.
Okay. This is a easy topic, you will get full marks for, you have one question from this one. Yes, like this, we can't change much. We can only change the numbers. Or maybe the calculation, this one calculation may be different. Okay, so you check your calculations for power, please. How did we get this? This is in the equations, but like the power in the so it's like in the equations there is the turn ratio is, you can use turn ratio NP over NS, and also P over ES, or else you can put the current in the opposite direction. Current is secondary divided by the primary, okay? Because the current current is when you have, yeah, the current should be in the opposite direction, isn't it? Am I right? If you wrote down the equations, it should be like this. So you can use find the current, and this one we already found it, and the voltage and the flux. Just you need to put the numbers in the equation, and you will get the magnetic flux. So that will be 3.6 milliwebers. Did you get that? No, these numbers are different. Am I right? No, it's the same numbers. 240. No, this number of terms. Yes, that's the same. Yeah. Are we good? Let me know when you finish, okay? Okay, next question. I'll give you time. It's a really easy part, so I'll give you time for you to do this. Try this.
Is this kind of questions going to be the test, or just the introduction to this question?
No, this is the type. These are the, like you get this kind of questions in the final exam. Yes, so it's easy one. Okay, so what did you do so far? Okay, an ideal transformer with 300 primary. So primary side NP is 300, and the EP is 240, and the frequency is 50 hertz. Okay, secondary side ES is 120, and the resistance in the secondary side is 60, connected across the secondary. How many turns in the, okay, so how many turns? So this one is dropping, isn't it? It is a step down transformer, half. So if you have 300 turns in the primary side, it should be half in the secondary side. Agree? 150, isn't it? And then they are asking how many turns in the secondary must have the output voltage, the current through the resistor. So how do we find the current? Current is equals to voltage divided by the resistance. So voltage is 120, resistance is 60, so the current is 2 amps. So if the current is 2 amps, what should be the current in the primary side? Current is happening opposite side. So if your number of turns are decreasing, current should increase. So your primary side current is 4 amps. That's good. Maximum flux is equals to 4.44 times frequency times NP EP, or else it is, if you want to use the secondary side information, that will be ES over 4.44 frequency times NS. So what do you get from this? When you finish, do you have the number? What's that?
3.6 times 10.
3.6 times 10 to the negative. Okay, so we can say 3.6 milliwebers. So do you all get 3.6 times 10 to the negative 3? Okay, that's good. Okay, we'll move to the next question. Can I move to the next question? Okay, let's move to the next question. Okay, so let's write down. So NP was 300, isn't it? NS was 150. We found it, and we got voltage. Secondary side current was 2 amps. Am I right? So the actually yes. So we made a mistake. So current is here. It is halving, and so current equation was like this. So IP over IS should be equals to NS over NP. So our IS is 2 and NS is 150 and NP is 300. So if you put these numbers together and if you make this the subject, IP is what? IP is NS times IS divided by NP, isn't it? So that will be 150 times 1 divided by 300. Sorry, 2, no, current is 2. So that will be 1 amp, isn't it? Am I right? Yes, so yeah. Yes, that's what happening. So your turns are halving, your current should be doubled. So 1 amp is doubling here. So this one is halving. So it's opposite actually. It's opposite. Yeah, what I have told in the previous one is wrong. So this should be 1 amp. It is doubling. This one is halving. So its current is opposite all the time. Okay, are we good now? Any question? Current is 1, yes. So see, because this one 300 is becoming 150, so 2 amps should be opposite. It should be like 1 amp is doubling here. This is halving, so it is doubling. Make sense? Are we good? Okay. Okay, so your primary number of turns in the primary is 300. Number of turns in the secondary, we need to find it. EP is 480 and the frequency is 60 Hertz. So in the secondary side, we know the voltage ES is 120 and the resistance is 100 ohms. So we can find the number of turns in the secondary, which is this one is divided by 4. So this should be, sorry, yes, divided by 4. So the number of turns also need to be divided by 4, isn't it? So 300 divided by 4, is that right? So that will be 30, 15, 75. Is that right? 75 number of turns. And current through the resistor, we can find the current through the resistor in the secondary, which is equals to 120 divided by 100, which is 1.2 amps. So the current in the primary, so if this is 1/4, we need to times this by 4. So IP times 4 is equals to 1.2. So we can say IP is equals to 0.3 amps. So flux we can find using the same equation. So flux is equals to let's take the the primary side. So 480 divided by 4.44 times the frequency is 60 times the NP is 300. So what do you get for flux? 6.01 times 10 to the negative 3 Webers. Am I right? Okay, that's good. So 6 milliwebers. 6 milliwebers. Okay, so with this we are finishing transformer questions, and transformer questions are really easy. You need to just you will get the equations. You just need to put the numbers, and you need to rearrange the equations and find the unknowns. Are we good? Can I move to the next one? Okay, now we are looking at the DC motors. So DC motors, you know, when we have, so motor means what I told you at the beginning. Motor, what the motor does? It is transforming electrical energy to mechanical energy, isn't it? So we are supplying an electrical energy, electricity. So we are supplying an electricity to this coil here. So we are supplying electricity, and we are keeping this coil in a magnetic field. So you having a current, and also this coil is in a magnetic field. So when you have a current in a current carrying coil in a magnetic field, what is happening? It is producing a force. Have you done that in your physics? So you have a current I is carrying here. So you have field lines north to south. So you can use again your right hand. So if you put the direction, if you keep your 4 fingers in the direction of your magnetic field and thumb in the direction of the current, force is going up like this. Or else you use this or this. So do you remember that? Have you done that in your physics? You should have done it, maybe forgotten. Magnetism or something. Okay, so there is you don't need any of these for electrical. Okay, so there is a force produced. So force produced, that force is this way up, and you can see the current in the other side of the coil is opposite direction. Current is in the opposite direction. Because the current is in the opposite direction, the force produced here is the opposite direction. So you have a moment, a couple moment. Am I right? Where did you learn that? In fundamentals of mechanics, which is good. So when you have a couple, what is happening? Is it in equilibrium or not? It's not in equilibrium. It is turning around, isn't it? Turning around, it's rotating. So that's how the electrical energy is converting to mechanical energy. So we supply a current, and we are keeping that coil in a magnetic field. Because of this force, couple force which is opposite in the direction, it is producing a couple moment, and this one is rotating. So that's how the electrical energy is converting to the mechanical energy. Do you understand that? Any question? Okay, so we'll move on to the next slide. Magnetic field we can produce a magnetic field in 2 ways. You can use a permanent magnet to create a magnetic field, and also we can have an electromagnet. What do we mean by electromagnet? Having a current carrying coil. Before also for transformers we discussed, when you have a current carrying coil, it produces a magnetic field. So this we call the electromagnet. So permanent magnets are good, but the thing is we can't control the magnetic field because it is a constant. But when you have an electromagnet, by changing the current and changing the direction of current, you can control the magnetic field. Am I right? So magnetic field, you can convert this one. I can't remember the exact, this H and the B. Depending on the current and the number of turns and this length, I don't remember this equation. So you can find this H, and mu times the H will be your internally induced magnetic field, and depending on the material that you have here, you can find that magnetic field. So those things are not relevant for us for this electrical, but you should have done that in your other subjects. Engineering materials, physics, everything is you have everything, you have done everything. Okay, now that's how the electromagnet working. So motor should have two windings. One is the field winding. Field winding is to create the magnetic flux. So it is like the magnetic field that we are producing, because we need to have a magnetic field. And also we have the armature winding. Armature is the one rotating inside a motor. So this armature, this part is the armature. So you can see that there should be two windings, armature winding and the field winding. Armature winding is to make the rotation, and the field winding is to produce the magnetic field. Are we good? So you can watch a video in the YouTube to how these motors work, and it is showing everything. So we don't need that part for here, so we'll move on. So we are going to learn just one type of a motor. I told you at the beginning. So DC motors, we can divide them into series motors and parallel motors or shunt motors. What is the difference between these two? Series motors means your field winding and the armature winding are series with each other. So two windings are series, that we call the series motors. Shunt motors are when the two windings are parallel. So we are going to learn just this one, okay? So we are not going to learn the series, and we are only learning this shunt motors. Okay, so this is the circuit for the shunt motor. So you can see we are supplying a voltage. So this is the line current, and current comes to a certain point, and it is going through the armature, and also it is going through the field. So you can see the field winding and the armature winding, two resistors are in parallel to each other. That's what we call the parallel or shunt motors. And we have the armature. There is a EMF induced in the armature, and this is what's happening. So you can, let's take the equations here. So what can you say about this? If you have a VT, supply voltage of total voltage VT, what is the voltage across these 2 points? VT, why is that? Because they are parallel points, parallel to this voltage. How about the voltage across the field? What is this voltage? Again VT. So those are known things. Am I right? And also if you this one, if you consider the line current is coming to this node, then divided between these 2 points. So this will be your armature current, and this will be your field current. So if you apply KCL to this point here, how can you write the equation? Current coming in, line current is equals to armature current plus the field current. Am I right? So these equations, you're going to use them. Are we good? And also if you apply, if you put KVL to this one, how do you write the KVL to that mesh? KVL is you're starting at a point and you're going around the mesh. So this is a negative VT, am I right? And when you're going to the current, this is the positive side, so positive IA times RA, isn't it? And you're going to this side, this one here, what is that? EA, that is the so this is also consuming energy, okay? So armature is consuming energy like the resistor. It is going into the positive side, so this is EA. So now if you make the EA the subject, you can find EA is equals to VT minus IARA. So you can use, so you don't need to remember this won't be given to you. You are applying the basic theories and you are going to find any unknowns, okay? So let's take an example and we'll see how you go. Okay, so this is where you have the no load and the full load, not in the transformer. So I told you during the transformer thing. So here you have 240 shunt motor. So we first draw it. Always draw it so that it is easier for you. So you have a field, and also you have this armature, and you have the field winding, So what they are saying, this one is 240 volts, and they say line current is 4 amps. The armature circuit resistance, armature is this one, so this armature resistance is 0.5 ohms. The shunt field winding resistance, this one resistance is 120 ohms. Sorry, ohms, yes. When the motor operates as a full load, it takes a current of so this 4 amps is the no load current. Let's do the no load part first. Okay, no load, I explained it like this. So you can have a let's take you have a fan. So fan have different speeds. No load means when the fan is switched off, it's not rotating, but it is still taking a small current. So that means the no load current. And full load means when you put the fan into the maximum speed, then it is taking the maximum current out of the source. So that will be your full load condition. So first do the no load. So can you find me these things? What is the field current? How do you find everything? I'll do the first one, no load, then I'll let you to do the field one, the full load one. So what can you say here? How do you find the current here? IF. Voltage across these 2 points is 240. Am I right? So the field current is equals to 240 divided by 120, which is 2 amps. Agree? Is it 2 amps? Okay, so if you apply KCL to this one, 2 amps going this way, so what should be the current in the armature? 2 amps. Agree? Are we good? And also, can you now apply KVL to this one? So you start at a point and you go around. So negative 240 plus 2 times 0.5 plus the EMF is equals to 0. Agree? So what is this one? 240 minus 1, which is 239 volts. Is this easy? They are really easy questions. Yes. What is the 2? 2 amps, yes. Voltage is current times the resistance. Is the 4 amp going across this, so 2 amps going across this? Only 2 amps going, isn't it? 4 amps is coming out from the source, that's right, but it is not, the whole 4 amps is not going through the armature. It is divided between the armature and the field. Are we good? So can you please do the full load? Only thing changing here is what? In the full load condition, you have 22 amps coming here. So you follow the same procedure and find everything. Okay? So I'll give you time. Yes, in the full load, that's like your fan is turning with the maximum speed. It is rotating fast, so it's taking more current from the source. No load means it is not rotating, it's just staying. But it is still taking a little current, maybe a small amount, like 4 amps. So what will be your field current? Is the field current changing or not? If you don't change the voltage, it doesn't change. Am I right? So what is your field current? Again 2 amps. How did you get it? 240 divided by 120. So what should be the armature current? It should be 20 amps, right? Okay, now when you apply the KVL to this one, how do you write it? Negative 240 plus 0.5 times 20 plus EA is equals to 0. So EA is equals to 240 minus 10, which is 230 volts. Are we good? IF doesn't change if you don't change the voltage. Minus 240, yes, because you're applying KVL, so you start at a point and you go around the mesh. So this is going into the negative side, so it is a negative 240. Coming into the positive side, supplying energy, so 240 is supplying, it's negative. Resistor is consuming and armature is consuming, so they are positive. Are we good? Can I move to the next question? You all done? Okay, let me know when you finish. Okay, so we did this. Okay, can you do this one, please? Okay, so we'll draw the circuit. So they are saying line current is 5 amps. And no load condition, armature winding resistance is 0.6 ohms, and the shunt field resistance is 80 ohms. The motor delivers its rated load with input power of 2.4 kilowatts. Okay, rated power, this one is for rated power, is for the full load, okay? We don't need this. And this is 240 volts. We don't need this for the first part, okay? No, for no load condition, we don't need this full load condition, like, you know, the power 2.4 is for full load. Okay, now can you tell me the voltage or else the current in the field? Current in the field is 240 divided by 80, which is 3 amps. Are we good? So what should be the armature current? 2 amps. And if you apply KVL to this one, negative 240 plus 0.6 times 2 plus EA is equals to 0. So your EA is 240 minus 1.2, which is equals to 238.8 volts. Okay. Are we good? Okay. Now how do you do the, any question? So when you do the full load, power is given to you. So how do we find the current? Line current in the full load condition. Power is what? Current times the voltage, isn't it? Current, if you divide the power by the voltage, which is 240, you can find the line current, which is equals to 10 amps. Is that right? Do you agree or not? Power is what? Current times the voltage. How do you know that? We learned it in the first week. Yes. You draw the circuit, it is easier for you to draw. It is easy if you draw the circuit. Yes, yes. So circuit, a simplified circuit for the shunt motor is like that. Your circuit will be the same. It never changes. Like, you know, for this one. Okay, so if this is 10 amps, what should be your armature current now? For the full load condition, what is your armature current? That will be 7 amps, isn't it? 2400, yes. 0.4 kilowatts, 2, 3. So the current is 10. Okay, so current is 7 amps, is that right? Did you get 7 or not? 2400 divided by 240, which is 10. Am I right, guys? Is it 10 amps? So then your armature current is 7 amps, is that right? And this is 10 amps. Now what is happening here? 0.6 times 7. So you can find this. Actually, I think this should be not 2.4 kilowatts. It should be about, it should be about 24 kilowatts. Because like, why I am saying that? Your full load, your no load is 5 amps, so full load can't be that small as 10 amps. I think the power here, it's a mistake in the question. So power, let's take the power as 24 kilowatts, because like, it should be very high. Like when you consider the full load, it can't be, no load is 5, so full load can't be 10. Full load, you should be more. So let's take this as 24 to make it more practical. So consider this full load power is 24 kilowatts. If the full load power is 24 kilowatts, how do you do this? What is your line current? 100. It is reliable. It is a practical value. So your line current is 100 amps. How did you get it? 2400. 24,000. You divided that by, you divided that by 240. So that will be 100. If this is 100, your armature current will be 100 minus 3. Makes sense? That will be 97 amps. So if this is 97 amps, now you can find the EA, which is 240 minus 0.6 times 97. So you find this, that is your voltage. Are we good? Okay. So yes, so this is a different question. Okay, so this is a different question. This is a different question. The answer is for different, full, I think full, in power you can find, if you know the current and the voltage, you can find the power. Yeah. Okay, so we'll move on to the next part. Okay, now let's see the generator. The generator, what is happening in the generator? What do we mean by generator? Generator is, what is doing by the generator? Mechanical energy is transferred to electrical energy, isn't it? So power supply is by the generator. So current should come out from the generator. Agree or not? So current should come out from the generator. You have the same circuit, only difference is now your current is coming out from the generator, not the current. Generator is not taking the current, it is producing the current, isn't it? So generator is producing a current and it comes to this end, and some of the current is taken by the field and some of the current is taken by the load, whatever the machine that we are connected in. So you use the same equations here. Only thing is your current is coming out from the load. So let's take an example and we'll do this question. Okay, can you try this by yourself? Then I will help you. Draw the circuit. Only thing is your current is coming out from the armature. So if you draw the circuit, you are not drawing a voltage source here. Instead of that, you have a resistor. So 240, the shunt generator. Resistor, okay, so this is 0.05 ohms and this is 40 ohms. The generator derives the rated load at the rated terminal voltage. The load current, which is this one, IL, we need to find it, and the field circuit, the current in the field, armature current, and the GE here. Okay, so they are saying power here. Power here is 24 kilowatts or 24,000. What should be the rest? So if the power is that, you can find the voltage here. Can we find the voltage? The voltage is given to us 240. So can we find the current? What is the current? Yes, 24,000 divided by 240, which is 100 amps. Okay, so 100 amps is going this way. And voltage across the 40 is what? Voltage here is what? It should be 240 because they are parallel, same as the previous one. So this should be 240 volts. So what should be the current? 6 amps. So 6 amps going this way and 100 going towards the left hand side. So what should be the armature current? 106. Why is that? It is, if you apply the KVL to here now, current coming in 106, 100 going in the left hand side, 6 going in the right hand side. Make sense? Now when you apply the KVL, you are applying the KVL in this direction, isn't it? Because the current is going that way. So the resistance positive here, negative here. Again, this one is a resistor, positive here, negative here. So your negative E is a supply energy now. So it's negative E plus 0.05 times IA plus the voltage here is 240 is equals to 0. Am I right? If you want, you can find the resistance here as well. Later on we'll find it. So E is what? E is equals to 240 plus 0.05 times 106. So you can find the voltage or the EMF generated by the generator. And if you want to find the resistance here, okay, so it's moved to here. So if you want to find the resistance, that resistance is equals to what? Resistance at the load, if they don't ask you to find. So you have here you have the voltage of 240 and the current of 100. So you can find the resistance if you want to, which is equals to 240 divided by 100, which is 2.4 ohms. Okay, if you want to, but it doesn't ask you to find it. Okay, are we good? Are we good? Any question? No questions. That's good. Okay, you can take a break and we'll do the rest of the question. This one and one more. So we first can draw the circuit. And this is 2400 kilowatts power, and the voltage is 120 volts. This one is 125.6 volts. Winding with the derived rated load, right? The field current is given to us, which is 6 amps. Okay, so we need to find the load current. We need to find this current IL, armature resistance RA, and the field resistance RF. Okay, how did you go? How do we find the IL? 24,000, you divide that by 120, am I right? That is 200 amps, isn't it? So this will be 200 amps. So what should this be? armature current should be what? 206 amps, that's right. And how about the resistance, armature resistance? If you know the current and if you know the resistance, if you know the, okay, so let's find the RF first. You know the current and the voltage, so how can you find the resistance? What is the voltage across the field? 120, so 120 divided by 6, which is 20 ohms, right? And you can apply the KVL to this one now. So that will be IARA plus 120. Now it is supplying energy. So when it is supplying energy, this 125.6 is negative, plus 120 plus 206 times RA is equals to 0. So RA you can find, which is 125.6 minus 120 divided by 206. So what do you get? It's a small resistance. What's that? 0.027 ohms. Okay, that's good. Are we good? Any question? Okay, are we finished? Okay, so okay, actually that's all we have for the questions. So as a summary, this is what we have learned today, right? So we discussed about the transformers. So transformer is a device which is we have input is electrical and output also electrical, but we can use it to step up or step down, or else sometimes just for electric isolation. So there are a few equations, and none of these equations need to be remembered. You will get all the equations, okay? But for motors and generators, you don't get these equations because you are just applying the basic theories. So what are the differences between motor and the generator? Motor is you need to supply energy to the motor to run, but generator is supplying energy by itself. So generator is supplying energy, but motor is consuming energy. So because of that, the current is going into the motor, and for the generator, current is coming out. Are we good? That's the difference. The circuit will look the same, but the direction of the current will be different. But here you have a voltage source to supply a current, and here you have a resistor to consume the current generated by the generator. Are we good? Any question? So that's all we have for this topic. So we'll wind up we'll finish this one here.